Welcome, curious minds, to a journey into one of nature's most deceptive phenomena, the slipperiness of ice. From the exhilarating glide of an ice skater to the frustrating tumble on a winter sidewalk, ice has a unique knack for defying our expectations of solid ground. It looks solid, it feels solid, yet it acts like a lubricated surface. Why? This isn't just a trivial question. It's a scientific puzzle that has challenged physicists for centuries, a beautiful example of how the most common things can hide the most profound complexities. For a long time, the prevailing theory was elegant in its simplicity: pressure melting. The idea was that when you step or skate on ice, the pressure you exert lowers the melting point of the ice beneath you. Even if the air temperature is below freezing, your weight would supposedly create a thin layer of liquid water, allowing you to slide. This theory, initially proposed by Faraday in the 19th century and popularized by others, seemed to make intuitive sense. A skater's thin blade, for instance, concentrates an immense amount of pressure, making the creation of water seem plausible. People walking, with their broader foot pads, would experience less localized pressure, but still enough, the theory suggested, to create that fleeting, treacherous film. It offered a neat explanation for a universal experience. But as science often does, when we look closer, the neat explanations sometimes unravel, revealing a much richer and intricate truth beneath the surface.
The pressure melting hypothesis, while compelling, has a significant flaw. Calculations show that to lower the melting point of ice by even a single degree Celsius, you'd need an enormous amount of pressure, roughly equivalent to an elephant balancing on a thimble. While an ice skater's blade does exert considerable pressure, it's generally not enough to melt ice at typical sub-zero temperatures, say -10 degrees Celsius or colder. If pressure melting were the sole cause, ice skating wouldn't be possible in colder climates, yet it is. Similarly, walking on ice at, for example, -20 degrees Celsius would be impossible, and yet we still slip. Clearly, something else is at play, or at least pressure melting isn't the primary mechanism. So, if pressure isn't the main culprit, what is? Another piece of the puzzle comes from a different form of energy: heat. When you move across any surface, friction generates heat. Think of rubbing your hands together to warm them up. The same principle applies to ice. A skate blade or a boot sole sliding over ice generates a small but significant amount of kinetic energy, which is converted into heat at the point of contact. This frictional heating can indeed melt a tiny film of ice, creating a lubricating layer. This is particularly relevant for high-speed activities like skating, where friction is more intense. However, even this isn't the whole story, because ice feels slippery before you even start moving on it. You can stand still on ice and still feel it ready to give way. This observation points to a more fundamental property of ice itself: the existence of a unique liquid-like layer that's present even when the temperature is well below freezing.
This brings us to the most compelling explanation for why ice is slippery: the quasi-liquid layer, or QLL. This isn't bulk water, but a thin, disordered layer of water molecules that exists naturally on the surface of ice, even at temperatures well below 0 degrees Celsius. Think of it like the very outer skin of an orange, which is different from the juicy segments inside. The QLL is only a few nanometers thick, unimaginably thin, perhaps just a few molecular layers deep, but it's enough to act as a lubricant. Why does this layer form? The key lies in the unique structure of water and its hydrogen bonds. In the bulk of an ice crystal, each water molecule is neatly locked into a lattice, forming strong hydrogen bonds with 4 neighboring molecules. These bonds create the rigid hexagonal structure of ice. However, molecules at the very surface of the ice crystal are different. They don't have the full complement of neighbors above them to form those perfect, stable hydrogen bonds. This deficiency means they are less strongly bound, less ordered, and more energetic. They vibrate more freely and can move more fluidly than their counterparts deeper within the crystal. As the temperature approaches 0 degrees Celsius, this disordered layer becomes thicker and more pronounced. Even at temperatures as low as -30 degrees Celsius, a very thin QLL still exists. It behaves somewhat like liquid water, but it's not quite a true liquid. It's a transitional state, hence quasi-liquid. This spontaneous formation of a slippery surface layer, driven by the inherent properties of water molecules at an interface, is the primary reason why ice is so uniquely slippery. It's an intrinsic property, not one created solely by external forces like pressure or friction, though those can certainly enhance it.
So, to truly understand why ice is slippery, we need to combine these factors. The inherent quasi-liquid layer provides the initial slipperiness, a fundamental property of the ice surface. When we add movement, whether it's the thin blade of a skate or the broader sole of a boot, friction comes into play. This frictional heating melts a little more of the ice, replenishing and thickening that crucial lubricating layer, making the slip even more pronounced. For ice skaters, the intense local pressure from the blade, while perhaps not melting ice at extreme sub-zero temperatures, can also contribute by locally concentrating forces that further disrupt hydrogen bonds and enhance the liquid-like behavior of the surface molecules in conjunction with frictional heating. This complex interplay explains the nuances of ice's behavior. At very low temperatures, say below -30 degrees Celsius, the QLL becomes extremely thin and less stable, making ice significantly less slippery. This is why polar explorers might find ice easier to walk on in extreme cold. Conversely, closer to 0 degrees Celsius, the QLL is thicker and more robust, and any slight pressure or friction easily creates a substantial water film, making ice incredibly treacherous. It's a delicate balance of molecular forces, temperature, and external interaction. The science of why ice is slippery isn't just an academic curiosity. It's a testament to the incredible complexity hidden within the simplest things. It shows us that even everyday phenomena, which we take for granted, are governed by intricate physical laws. From ice skating championships to simply navigating a winter morning, understanding this science allows us to appreciate the subtle beauty and profound engineering present in the world around us. And it reminds us that even in the seemingly mundane, there's always more to discover.
Subscribe to the channel and hit the bell icon for more amazing content.